I am going to discuss about residual property, that is also known as departure function. Students might be knowing about residual property, but they don't know about the significance of residual property, where they have to use and what are the applications of residual property. They can use residual properties in a simple problem solution. I have considered one motivational example before starting the conceptual understanding of residual property. In this problem, the statement is something like CH4, that is methane, and if we talk about CNG, compressed natural gas, CNG contains major portion of methane and a trace amount of other ethane. CH4 enters a compressor at T equal to 20 degrees Celsius and pressure P, that is 1 megapascal. This is a compressor and it is compressed up to 25 megapascal, that is the outlet pressure of the, I have considered this one is a example of CNG, compressed natural gas. This would be the pressure while we are compressing natural gas. In the problem statement, we have to calculate how much work is required per mole of gas. This is a compressor, so work is required. If it is turbine, then work will be produced. Here, we can use property data sheet if we require any property, such as for example Cp, specific heat at constant pressure. We can take from the literature, as well as if you want to use any equation of state, then something like if I want to use any van der Waals equation of state, then I can take the value of van der Waals parameter from the property sheet. But how to solve this problem? That is the question. Means can we solve? Means how we can solve? From the basic thermodynamics, I can tell that this is a flow system. If you apply first law of thermodynamics to flow system, then the equation would be something like Q plus Ws equal to G delta Z plus delta U square by 2 plus delta H. You might be aware about all these terms. Q is the if there is any heat absorption or heat rejection. Ws something like shaft work is added or it is produced. G delta Z, that is the difference in potential energy, and this is something, this term is related to kinetic energy change. And delta H, then what is the enthalpy change. In this case, if I consider, if I can assume as for example it is steady state, this equation by the way is valid only for steady state. If there is unsteady state flow system, then this equation is not valid. Steady state, then the other assumption is something like adiabatic compression, means that there is no heat loss or heat rejection. And the third assumption is potential energy change and kinetic energy change are negligible. So these are the some changes in this equation, and I am going to cancel these two terms. So ultimately Ws equal to delta H. This is the same equation for adiabatic turbine, only the sign of the work would be different. Means the same equation we can also we can use for the calculation of work using turbine, and in that case also we are assuming that it is an adiabatic expansion. So this is the equation Ws equal to delta H. Now how to calculate delta H? That is the enthalpy change between two states. So this is state 1 and this is state 2. So what is the enthalpy change between these two states? I can write in this way: if T1 P1, T2 P2, delta H equal to dH. Means I need to know enthalpy at this state, enthalpy at this state, and I can take the differentiation of this equation, that is dH, and from the fundamental property relation, and if you remember, the equation of dH is something like Cp dt plus V minus T del V over del T at constant P dP. This was the equation in it is derived in previous video. Enthalpy as a function of two canonical variable, that is T and P. If I want to use this equation, then I need to know the value of Cp, and the value of Cp, or I can say the Cp is a function of temperature and pressure. Is it? Or Cp is a function of temperature only? Okay. Cp is a function of temperature only for an ideal gas. But when we talk about real gas, it is a function of both temperature and pressure. So if you are planning to use this Cp, is something like Bt plus Ct square. This type of equation you might have used somewhere. You can't use this equation because this is valid only for an ideal gas. If you are going to use if you are going to solve the problem for real gas, then we can't use this equation. So here the question is, the pressure is 25 megapascal, which is too high. At this much pressure, we can't use, or we can't assume the state of a gas is an ideal gas, because pressure is much high. So we have to consider this problem as a real gas. You can't use Cp as a function of temperature for real gas. So what is the strategy? How will you solve this problem? For that, if you could solve this problem by ideal gas, assuming an ideal gas, and then you are shifting towards real gas, and if you know two things, as per example, I am assuming that at this much pressure and temperature, at this much pressure and temperature, the state is an ideal gas. I can use those equations, I can solve the problem using an ideal gas, then I can just move that state or move the entire problem in real gas, and we should know the difference between these two. What is the deviation, right? So residual property, that is something like the difference between property of real gas and property of ideal gas at the same temperature and pressure. Whatever property you are measuring, temperature of real gas at temperature and pressure, the same property we can measure for an ideal gas, but the temperature and pressure should be the same. So I can also write this in this way: mTp minus Miz Tp. So the meaning is, we have to consider same temperature and pressure, and that is the real gas. So in case of ideal gas, we can solve the problem, but if we are able to know the value of this, then we can easily shift to the real gas, and we can find the value of or value of any Ws considering real gas. So residual property shows the deviation of real gas from an ideal gas. So this is the second parameter. One more parameter is compressibility factor. If we talk about ideal gas, then compressibility factor Z equal to 1, and for real gas Z has some value. It may be something like 1.2 or something. So Z also shows the deviation from an ideal gas. Residual property also shows the deviation from ideal gas. That was the motivational example for residual property, but what is the significance of residual property? I have just drawn one diagram. Suppose if I consider pressure and temperature, and this is the real fluid, this is the, as for example, the state 1, something pressure P1 and temperature is T1. I can just denote state 1 here. During the process, it is the final state is something here, that is as for example P2 and T2. How we can calculate the property between these two states? As for example, I want to calculate delta U. So here U1, here suppose U2. What is the change in internal energy during the change in the state 1 to state 2? And I am talking about real fluid property, not ideal gas. So what is the solution strategy, how we can solve this problem? We don't have any equation that can directly give the U1 and U2 difference for real gas, but we know the equations for an ideal gas. So here what I am going to do, I am assuming the same pressure and temperature state 1 and state 2, considering that real gas. So this is again state 1. I am assuming that considering as an ideal gas, not a real gas, sorry. So P1, T1. So what we have to do, we can move from this state to this state. So we are just moving from real gas to an ideal gas, and this difference, that is M minus MIG, that is at state 1. We are talking about state 1, and this is I am considering minus right now. So this is the change in the state 1 in real gas as well as in the ideal gas. This difference, that is the residual property. Okay, same thing I can write for this one also. The difference between these two point, that is M minus MIG at state 2. If I am considering this is positive, then this would be negative because I am shifting from real gas to an ideal gas. Okay, and what is the use of this one? Okay, if I am reaching from this real gas to an ideal gas, and I am considering the final state is this one, so I have many equations for ideal gas, right? Suppose isothermal, then isobaric. This is the one way. So from this pressure, temperature to this, means we have the equations for isobaric, then adiabatic, then isothermal, isochoric, means the properties equation for an ideal gas. So that difference we can easily calculate it, we can easily calculate, and this would be the final state. So at this final state, we would be able to calculate, yeah, this is Ig, then U2 Ig, U1 Ig. This is the final state of internal energy, but we want the answer in real gas. So again we have to shift from this point to this point, and that is again residual. MR2, this is MR1. M is any property. Here we are talking about internal energy. So from U2 Ig, if we have calculated U2 Ig, then again we can shift to the real gas, and these two difference should be known, MR1 as well as MR2. If we are able to know this residual difference, then we can easily calculate the property change in real gas. Now the question is how these are known if you don't know the value of M and MIG. There are many equations from where we can get the MR value directly without knowing these two values. If I write the equation, or I am assuming that internal energy change, I want to calculate delta U, that is U2 minus U1, means the internal energy at state 2 minus internal energy at state 1. So I can just write this equation entirely in this way: u2 minus u2Iz plus, so I am shifting in this way: u2 minus u2Iz, then u2Iz minus u1Iz, the difference is between these two, plus again, or we can take minus u1 minus u1Iz, u1 minus, or plus also we can take, that is something like u1Iz minus u1. So that is the difference between these two. And now what is this equation? This is m minus Mig, that is equal to Mr. So I can write Mr2, this is delta U Iz, because both internal energy have been calculated using ideal gas state, and it is U2 minus U1. So that is delta U. Again this would be M1R. Real gas property minus ideal gas property for the state 1. And this can be again written, so I am writing in terms of U, sorry. So this U2R minus U1R, that is again delta UR plus delta UIZ. So this is the one equation. And the other, if I want to calculate property change for any real gas, then I need to know two terms. The one is change in the property for an ideal gas, and the other is residual property change, means what is the deviation between real gas and ideal gas, and that can be added. Both property changes can be added, and delta U can be obtained. So this is the importance of residual property, because students know the definition of that why they are studying the difference between these two. But I have explained earlier that if you want to calculate the difference between two values, something like internal energy change between two states for real gas, then you can apply the equations of an ideal gas, but you have to add some correction factor, and that is the residual property, because we don't have developed equations for something like for real gas property change. So we can apply ideal gas equations for the calculation of changes in property, then we have to just correct that term by residual property, and residual property can be obtained by something else. Maybe there, if you know the value of compressibility factor Z, then we can also obtain the property change of residual property. Thank you. Thanks for watching this video. Please subscribe to my channel.